Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to do a practice problem on reaction mechanisms. So I have this proposal of a reaction mechanism, and remember, our job to say, hey, this is a valid reaction mechanism, or we can say it's an invalid reaction mechanism. And to become a valid reaction mechanism, you got to pass two tests. You got to pass the stoichiometry test, and you got to pass the kinetics test. Now, the stoichiometry test is simple. Okay, all you have to do is add these two chemical reactions together, and if it equals our overall chemical reaction, okay, that I have here in blue, okay, then it passes the stoichiometry test. So let's do that part first. We're going to add these two chemical reactions together. And when you're adding chemical reactions together, all you have to do is put all the reactants on the left-hand side and all of the products on the right-hand side. So let's go ahead and do that. NO2 and NO2. And then NO3 and CO. Those are all the reactants, okay, and they're on the left-hand side. And I put these four products on the right-hand side. NO3, NO, NO2, and CO2. And of course, we're going to cross out anything that's the same on both sides. I believe the NO3 is the same on both sides. And we have an NO2 on both sides. And so we end up with the chemical reaction of NO2 and CO yielding NO and CO2. And our job is, does this match the overall balanced chemical equation? And when we look at it, it looks like everything matches up, so it passes the stoichiometry test. When we add these two things together, okay, it equals our overall chemical reaction. So it passes the stoichiometry test. Now, let's see if it passes the kinetics test. Now, to pass the kinetics test, okay, the rate determining step, which is going to be the slow step, their kinetics have to match the observed rate law for this chemical reaction. So to figure out what the observed rate law is, okay, we're going to use experimental data. Okay, so we're going to label this as what we observe as the rate law. And the rate law is going to be equal to K times each of the reactants, NO2 and CO, to a particular order of X and Y. And we're going to use this experimental data to figure out what X and Y are. Now, this is in a previous video, but we're going to do a quick review here. Okay, what we're going to notice is that the NO2 does not change concentration, but the CO is being doubled from 0.15 to 0.30. And what we do is we're going to look at the rate change as this CO is doubled. So as CO is doubled, the rate stays exactly the same. So concentration is not a factor when it comes to CO. So that's going to be a rate order of 0. Okay, and then we're going to do the same thing for the NO2. The CO between experiments 1 and 3 is constant, so it's not a factor. And in between experiments 1 and 3, the NO2 is being doubled. Okay, well, when it's being doubled, the rate is quadrupling. If the rate quadruples, that means that this thing has a rate order of 2. So the observed rate law is that the rate is equal to K times NO2 to the second power. And remember, anything to the 0 power is simply 1. So really the rate law, we could just kind of X this out, okay? The rate law is equal to K times NO2 to the second power. Now, if this proposal, okay, is valid, it has to match that observed rate law, okay? Now, what you do is you look at the different steps and you find the slow step. And remember, we call that the rate determining step, the RDS, okay, the rate determining step. And that slow step, its kinetics better match my observed rate law if this reaction mechanism is valid, okay? Now, since this is an elementary step, okay, we simply can look at it and determine the rate law. It's going to be rate is equal to K times all of the reactants. So that's NO2 times NO2, or simply NO2 to the second power, okay? So does this match this? Yes, it does. So when the slow step is first, when this is the rate determining step, we have we can say that this reaction mechanism is valid because it passes both the tests. It passes the stoichiometry test, where when you add things up, it equals the overall chemical reaction. And the slow step, or what we call the rate determining step, its kinetics matches what we observe, okay, as a rate law when we look at experimental data. So this is a valid reaction mechanism, okay? I'm going to do a what if now, okay? So I'm going to kind of change the problem a little bit, okay? I'm going to reverse these two from slow to fast, okay? So I'm going to make, instead of the slow step being first, where we get a valid, so I'm going to leave this when it's slow step first, the reaction mechanism is valid. Okay, we're going to see what happens if we reverse this, okay? What happens if we said that this was the fast step and that this was the slow step? So that's kind of the what if that we're going to talk about. Well, if that's the case, okay, this thing still passes the stoichiometry test because everything adds up. So I'm not really worried about that, okay? But now we need to check the kinetics because this is the slow step now. So the rate is going to be equal to K times NO3 and CO. And if you look right here, the NO3 is an intermediate. And right now you might say, hey, these kinetics don't match the observed rate law. You might say that this is invalid. And I agree with you 100%. Okay, that's what's going to happen. But what I want to do is make sure that we know how to practice these harder problems where slow step is second. Okay, so let's kind of work with that. So I'm going to erase the stoichiometry piece here just so I have extra room to work with. And the process that you work with when the slow step is second is that a lot of times you'll get an intermediate in your rate law, and intermediates are not allowed to be part of the rate law. So what you have to do is you have to put this first reaction in equilibrium, and you got to say that the forward reaction is just as fast as the reverse reaction. So going forward, okay, if I was to write the rate law for it, it would be this, because this was the forward rate law. So rate is equal to K times NO2 squared, okay? But going backwards or reverse, okay, if we're saying it can be in equilibrium, it can work in the reverse direction, then these are the reactants for the reverse reaction. So rate is equal to K, and these guys, NO3 and NO, are going to be part of the rate law. And if it's in equilibrium, we say that these rates are equal to each other, okay? So what we're saying is that the forward rate, K times NO2 to the second power, is equal to K times NO3 times NO. We're going to say that K is going to cancel out just for simplicity reasons, okay? And then what we're going to do is we're going to solve for that intermediate. So we're trying to solve for this guy. And the way we do that is by dividing by NO on both sides. Now, typically, we won't leave things as a denominator in here. So mathematically, if we made this a numerator, the NO3 is going to be equal to the NO2 to the second power. But if we want to move this up to the numerator, this is what it's going to look like. So NO3 is going to be equal to the NO2 to the second power. And if we bring this up to the numerator, the math that ends up being is we say that that's to the -1, okay? So what we're going to do now is we're going to substitute that in right here for the rate law, okay? So this rate ends up being equal to K times NO3, which is equal to these two things, which is NO2 to the second power, NO to the -1 power, times the CO, And this is going to be the rate law if the second step is slow, okay? And now we can say, oh, look, okay, this does not match the observed rate law. So this is an invalid reaction mechanism when the slow step is the second step, okay? So if it's slow step's the first step, we match and we say that it's valid, okay? But if we say that the slow step is second, okay, we get this as a rate law, and it does not match the observed rate law, and therefore we say the reaction mechanism is invalid, okay? So I guess this comes down to when the slow step is first, it's really easy. You just kind of compare them, okay? But when the slow step is second, those are the hard problems. And I just want to review what we did. We write the rate law and realize that we have an intermediate, okay? And that intermediate has to be substituted. So what we do is we put this equation in equilibrium, and the forward reaction is just as fast as the reverse reaction. So we write the rate laws for each of them, set them equal to each other, and then we solve for the intermediate, okay? And after we solve for the intermediate, we then substitute it back into the rate law and then check to see if it matches the observed rate law. I know that was a lot, okay? I get that, but I wanted to make sure we did this as a practice problem so that you can see how to go through the steps of putting this first reaction in equilibrium and doing the substitution, because that's the hardest part for students when it comes to reaction mechanisms. So once again, if the slow step was first, okay, it's a valid reaction mechanism. Everything matches up, the stoichiometry and the kinetics, okay? But if we made the slow step second, the stoichiometry would match, but the kinetics would not, and therefore would be an invalid reaction mechanism. If you found this content helpful, give it a like and subscribe. And when you leave a comment, it pushes this information out to other students that might be interested in learning chemistry.